Yeah.
All right. So hello everyone. Welcome back to the ARC seminar. Today we have Rhiannon from the LIGO group, and she's going to tell us about LIGO detectors.
All right. So this is going to be a focus on LIGO detectors. So I'm Rhiannon. I'm a third-year graduate student, but I do data analysis and parameter estimation. So I wanted to take the chance to kind of learn some things about how the detector actually works, since that seems like maybe a thing I should know. So I'll be presenting that. So, okay. So basically, whenever people describe the LIGO detector to you, or at least to me, they always just talk about a Michelson interferometer, which is good. Well, all well and good, but they're rather more complicated than that. So I'm going to be trying to go a step past that. And there's this review article by Bond and some other people. And this is what I'll be following pretty much directly. I moved things around, I summarized, but that's what this is. So I strongly encourage you to go read that review article if you're interested. It's good, pretty thorough. So yeah, but part of that is I am going to include introductions to cavities, to detection schemes, noise sources, which is not really mentioned, at least in my experience, when people talk through like basic intros to LIGO. But I will not be mentioning, among other things, control systems, which is like 70% of it. So that, don't take this as all there is. If you want to talk about control systems, just ask Ethan. He'll have fun talking about it. Anyways, and also mode cleaning. So it's all magically about Gaussian beam. Don't ask how about that way. Okay. So with that all said, let's get into it. So we're going to start, what is sort of, for people who may not have taken a GR class, what are gravitational waves? So this is the strain sourced by the quadrupolar moment. So gravitational waves are the instantaneous strain on space-time. And they're sourced in this way. So the important bits of this are two things. Firstly, do you ever see the force? It's a small number. So every mass quadrupoles are rather obviously changing all the time. So gravitational waves are being sourced all the time. But unless that mass quadrupole change is very large, they're tiny. And the second thing, though, which is astrophysically interesting, is that the scaling of strain is 1 over luminosity distance instead of 1 over luminosity distance squared, like it is for most electromagnetic sources. And that means that the visibility range of gravitational wave detectors, especially in the future, in the next few decades, has the potential to be much greater than you could normally achieve with EM observation. Okay. So briefly, to give a sense of the scales, we're looking at about 10 to the minus 21. So whenever you see a plot about sensitivities, something has to be at, or the signals themselves will be at about the 10 to the minus 21 level. So you want to have noise below that level if you want to see anything. Okay. So now let's talk about basic optics. So this is stuff that feels like it should be taught in an undergraduate course. Maybe it is, but I was not in mine. So I'm going to just briefly go over it. I guess some of it was taught in 136A. I'll give Sterl that credit. Not that I understood it, but there you have it. Okay, so we have our electric field from a laser beam, and we're going to absorb the phase and the amplitude into E naught. And we're going to have the propagation with distance based on some wave number. All well and good. Okay. So we want to know two things. We want to know how fields propagate, and we want to know how fields interact with mirrors. Obviously, fields can do other things. We will not be discussing that here. So a mirror. This is very cool and normal. You have field come in. It goes to the mirror. Part of it is transmitted, and then it may have field coming from the other side, part of which will be transmitted, and then the rest of it will be reflected. Okay. This is the linear systems of equations to describe that. So here you have it, and you can do math. You can write a matrix equation. That will be useful later. Moving on. You can also do the same thing with space. Light propagates through space. It gains a phase. You can write down a matrix equation. Moving on. Now, if you do a slightly more interesting thing, you put a mirror, then space, then a mirror, and then you get this. So this is sort of prototypically a two-mirror system, and you can make every Perot cavity out of it. So, the convenient thing about matrices is you just put them all there and you multiply it, and you get this. And this lets you get an equation for the transmitted energy over the input energy. So this is what I said. Oh, sorry. Okay. You have this equation. This will be useful later. But the important bit, of course, is you gain phases, and sometimes phases may equal 0. Or, well, an integer multiple of 2. Okay. So fabric Perot cavities have some interesting properties, which will be useful. Have a free spectral range. This is the place where you have integer multiple of 2 pi is the phase gain from traveling a length. So you have interesting properties. You can also talk about this quantity, which is mostly of interest to define this next quantity, finesse. So a high finesse cavity is one where the mirrors are very reflective, so you get a lot of bouncing going on. And yeah. And this is sort of what that looks like in terms of the frequency dependent effects of the fabric Perot cavity on the inner. So this is to say, for how, if you input 1 watt, how many watts do you get out? I'm not sure what frequency this for. Should have written down what length this fabric Perot cavity is. You could go find it, I suppose, by looking at these numbers. But anyway, so you can see you have these resonance spikes at the free spectral range as their period, and you have these very, very sharp resonances, and you also have anti-resonances. Okay. So now, let's talk about the other important thing here, and that's Michelson interferometers. So I think people have probably heard of these before, but I'll go briefly. So Michelson interferometers allow you to measure the differential arm length as opposed to something else like the common length. And they work by, you take a beam, you split it, you send it along perpendicular arms, you bring it back together. And so if these beams in traveling along these perpendicular arms gain a different amount of phase, then when they recombine, they may be out of phase. And so if that occurs, they'll destructively interfere instead of constructively interfering to the point where it's possible to get fully no light at all. Okay, so this is useful because this is very sensitive. This is destructively this is sensitive to differences in the distance traveled on orders less than the wavelength of the light, which is a good start. Okay, so this is a brief schematic of what this looks like. So we have beam incident on the beam splitter. Part of it gets reflected, goes up to the Y arm, bounces off the end test mass, comes back, transmitted to this, the output port. The other beam, it's transmitted through the beam splitter, reflects off the X test mass, bounces back, reflects, and then these recombine. And then these recombine at the output port. Okay, so you can do the same matrix thing that I will not be writing out, and you get an output field that looks something like this. You just recombine. You have these phase differences from the transmission, from the reflection, and from the propagation. Okay, so we have this convention that we'll be using to simplify things. It's essentially, we'll give a phase shift of pi over 2 if we transmit, we'll give a phase shift of 0 if we reflect. Just makes it easier. Okay, you can write this down then in terms of the common phase and the differential phase. So the common phase is to say, the mean of the phases. The differential phase is their difference. Okay, so let's look at briefly what that means for CARM and DARM, which is to say the common arm length and the differential arm length. So this is the average of the arm lengths and the difference of arm lengths. Okay, so we write down what we had before, but we substitute in the Y arm length and the X arm length. And then we can write this down. We can do the solutions. There's some math here, but power is this. You plug in, you do your algebra, and you come out to this. And the important bit here, right, is that you have this cosine square on delta L over lambda. And so if delta L over lambda is a, what is this, quarter integer, then you end up with dark fringes. So this is relevant. Okay. Now, let's go into how we actually detect the gravitational wave signal. Oh, it's 10 minutes. Okay. Cool. So let's first talk about phase modulations. Another thing that seems like it should have been taught in an undergrad class, but was not taught to me at least. And also Sterl didn't teach this. So this is a phase modulation. Basically, you have signal like this, or a modulating thing onto your carrier signal, which has a central frequency here. So you have a single frequency, and it's going to get modulated. Okay. And we're going to specifically talk about the case where m is small. So you can do some approximations with Bessel functions, and you end up with something that looks like this. This is the second order. So yes, an infinite sum. The important bit here is that you have these sidebands. So weirdly, or I guess it's not weird, but you end up with both a positive and a negative sideband. So as to say, kind of briefly, you have your central frequency here. This is omega naught, and then you have omega naught plus omega, and omega naught minus omega. Right? Some of the power goes from this central beam in frequency space. Some of the power goes from the central beam into sideband. Okay. Why does this matter? Well, it matters because, in fact, gravitational waves do a phase modulation onto our carrier beam. So we will detect gravitational waves as a phase modulation. And they'll give rise to these signal sidebands. So what that looks like is this. So this is a slightly subtle thing. So I'm going to go ahead and draw this one on white. Okay, so if I have this beam, okay, I'm not going to worry about blazing light. This is a carrier beam. It hits my photodetector here. This is a phase shift of 0. Then it bounces off a mirror, phase shift to 0, transmits, phase shift higher 2. Okay, so this stretch that went along the y-arm has gotten higher to this stretch gets transmitted. Transmission gets a phase shift higher 2, bounces, collection gets a phase shift to 0, bounces again, collection gives a phase shift to 0, recombines. Okay, so basically, moral of the story is, I have something coming from a laser, it is going to be given the same phase shift traveling along both arms, so it'll just even out. Okay, which means that if both arms are the same length, then we'll have constructive interference. By contrast, gravitational wave signals will only affect, or the sideband will only be generated in the arms. So that means that I have this extra thing here going like this, and then coming back around. So when this one comes around, it will get a phase shift of pi over 2. When this one comes around, it won't get any phase shift. This phase shift will be 0. So the signal sideband will actually, if the arms are exactly the same length, they'll actually perfectly destructively interfere. So that's what this plot is showing. Is the not quite sure what the units they used to generate this plot were, but you can see the signal sideband zeroes out when the Michelson tuning is set to 0. That is to say, if the arms are the same length, or well, the same length modulo the wave frequency, or the carrier frequency. And then by contrast, when the Michelson tuning is set to here, which is so 90 degrees, then the carrier goes to 0, but the signal but sidebands reach their maximum. So this implies that we can get sort of minimum power on the photodiode from stuff we don't care about, the carrier, while maximizing the power from the signal if we're at the dark fringe. But there's a catch to that we'll get into in just a second. So the catch is that we have the signal sidebands are themselves very small. They're best observed as a beat on some other some other oscillator. So in order to observe them, we need to have something for them to beat against. And there are a lot of different ways that you can do that. But the one LIGO uses is a DC offset scheme. So as to say is that instead of being at the dark fringe, we sit very slightly off the dark fringe. So this is the sort of operating point delta L, and that means that you can do some math and plug it in, and you get something that looks like this. So the important bit here, or sorry, okay, yeah. So when you get a field that looks like that, and then when you take your squares, or well, times complex conjugate to get the power, you see this, right? So the order of signal sidebands is going to be very small. So the signal sidebands are observable here in this first order against the delta offset. So if you took the offset to 0, you actually wouldn't see the signal sidebands observably. Okay, so this is the basis of why we would choose to do this Homodyne scheme. Homodyne is the right word, right? This is what Derek has told me. Okay.
I guess that makes sense because in radio, heterodyne is you're introducing another carrier.
Yeah, so that is another option you can do. So some of the other schemes include RF modulating the carrier to give you sideband that you would have. There's another scheme that involves setting up another oscillator. I'm not quite sure how that's done. There are good technical reasons why people chose this, is I think the thing to say. But you can't, this is not the only way to make a detector, but it is how LIGO have chosen to make a detector. Please do. Yes, I'm sorry, I've been one. So
Why do the path lengths change?
we will get to that. Actually, no, I guess this is not strictly written out, so I should write this. So gravitational waves, for those who may not have interacted with them, are something like, well, there are distortions in space-time, right? So imagine I have a perfect gravitational wave. The two polarizations are something like, this is a very goofy they're not this much, but they look something, you can have two. So you have, this is called the plus, and this is to say, this will stretch while this one shrinks, and by stretch I mean literally space is longer, right? This one's stretching while this one shrinks, and then vice versa. That will be relevant near the end of this. And then you also have a second mode that is the cross polarization, where this is happening there. So they're stretching, and the two axes are stretching together. Okay. So for reasons, the gravitational waves are tensorially sourced, but GR actually over-constrains it, or constrains it significantly, such that you could have 9 polarizations, but GR only allows 2, which are these. So there's also some other stuff you did called going to transverse traceless, where it's not what I'm going to talk about. Point is, if I have a gravitational wave that conveniently has exactly the plus polarization, and is exactly at this angle, and is exactly overhead my detector, is literally going to just do this. It's going to take the Y arm and push it down while it stretches the X arm, and then together.
So I don't know if it's probably not called a pointing vector, but in EM it's a pointing vector. So, but in this case, the propagation direction for you to detect it needs to be orthogonal to the arms of the interferometer, or no?
If you have, we have no sensitivity in the plane of the interferometer.
Well, there's
Do
a
we?
few points in the plane, right? So you can like draw the same picture of this ellipse, right? Stretching and squeezing. So it came at a like 45 degrees to the arms. You affect both arms simultaneously, so you actually do some change. You can do that, at each plane. But then you can come down on like one arm will move, the other arm will move. So then you can detect it down a length one arm, you've got that sensitivity because only half it is.
Right.
And then obviously like you can just pick any arbitrary combination of like directly above, to the side, like around, and you get like a map of what intensity are different.
Mhm.
So the amount of power, you can also do this in like particular polarization.
Yeah, so the math I'm gonna do is gonna obfuscate the directionality of this. We're just gonna plug it away. But yeah,
I guess my other question was like, what order of so you're receiving the laser with a photodiode. What kind of order of magnitude voltage do you know? Like how crazy is the electronics of the receiver?
no, I don't actually know this
It's
off
like
the
a
top of my head.
huge laser, right? Like,
Yeah. It's like 70 out, but then it's like amplified up to like.
Yeah, the circulating power is in the hundreds of kilowatts. So. Yeah. But the point is that you are, because you're operating near the dark fringe, right? Almost all the carrier power is getting
right.
canceled. Yeah. Yeah, and conveniently also almost all the laser noise is also getting destructively interfered by this process. The laser noise is not a significant concern.
It's the same laser when
Yeah.
they're BDS, so.
Okay, cool. Any other questions? I'm going very fast, so we have plenty of time for questions. Okay. So let's talk about the simplest possible gravitational wave. Because I guess you would call it a continuous wave source at a very lucky polarization and position. So basically, you can compute the phase shift for this. It looks like this. You do this integral, and you do it, and it looks like that. All well and good. And so this phase shift will produce. Sorry.
That's the phase shift of going down the arm once.
Yeah, this is the phase. It's actually the phase shift. Yeah, I guess it is once down. Yeah. And yeah, it has to be for a reason we'll get into in a second. So you can write down the you can go back to the phase modulation equation we had earlier, and you can correspond these things to those things. It looks like this. And then you can do some math to get out this quantity, which we will use a bunch immediately. Okay, so yeah, math, there you go. Here's what the schematic of this is gonna look like. So the important bit, so we have, carrier beam enters the arm, all well and good. In the process of getting to the end test mass, it's going to have some phase modulation by a gravitational wave being incident on it. So we're going to get this sideband, and then we're also going to still have a bunch of carrier power. And we're going to get reflected off the mirror. So we'll have the phase shift associated with that. And then we'll come back along and B2. So B2 will have a propagation. B2 will itself be affected by the propagation. So we'll gain a phase shift, and then also the gravitational wave is still happening. So A2 more power will also couple out of A2 and add on to the band. So we'll get this sideband here. It reflects both trips down the arm. That's why also we had the heat as well. Okay. So you can write out the linear algebra for the systems of equations for this. It looks like this. With predictably lots of fun little things happening here. And then you do some math, and it looks like this. So yeah, so the important things here, you have both phases due to this is sort of the carrier, right? This is the carrier's wave number and the length, and then also stuff from the wave number of the gravitational wave. Yeah. Gravitational waves, I guess, for anyone who's not aware, propagate the speed of light, so how you get the wave number. Okay. Any other questions or questions about what any of these variables are, since I didn't actually define any of them? Okay. So now we want to ask, what is the power on the photodiode? So the power is going to combine from the plus and the minus sideband of each arm, right? So you have to take all those into account. In particular, the X arm and the Y arm will have traveled different lengths. And then also, this is sort of our pledge for how the polarization works. We're going to say that the X arm gets a negative sign with respect to the Y arm. Okay, and so we can also then, as another step, we're going to want to switch from length. So we'll want to substitute in LX, LY, and then switch to the common length and the differential length. And you do that. Well, it looks like this. Okay, so this is all well and good. This is the carrier field. This is the power or the field of the carrier, and this is the field of the sidebands due to gravitational wave modulation. Okay. All well and good. You take the power, and you can compute this transfer function. Okay, so guess I didn't really offer anything worth asking a question about, but any questions? All right. So, yeah.
So why is it only one photodiode? Like why not measure both sides? Oh, I guess it's a laser.
Yeah.
Right.
Yeah, there's also some cavities in the way that we will get to in a moment. Yeah.
The light is reflected back from the one with the CARM.
Yeah. Okay.
Okay. So now let's talk about some of the sources of noise that can occur within the detector, because they're kind of important to understand the last, I think, most important bit of this, which is why do we do a bunch of the things we do in modern detector design. Okay, so first we can talk about shot noise. So this is vacuum fluctuations coupling onto the carrier beam. So they have this PDF. This is you derive this with some quantum. It's also surprisingly similar to the classical derivation. But the relevant bit of this is that you can see it depends on carrier frequency and carrier power, but nothing about the gravitational wave frequency. If you want to compute the noise to signal ratio, which is to say the thing we're trying to minimize, you can see that this has, we're going to use a transfer function from the past. You can see it looks like this. So it depends as 1 over the root of the power, and it has this dependence on the gravitational wave frequency. So this is nearly flat for very low frequencies, and then it starts to go as you reach towards the resonance, you start to get a much higher. Okay, all well and good. Let's look at what that's, or we can see what that looks like here. So this is, I don't know why I did a 1 kilometer arm detector, but anyway, so this is the bit where you have omega GW over sine omega GW with some other stuff. So this is the free spectral range, and it defines these don't particularly matter for LIGO, but they would matter for Einstein, or for Cosmic Explorer Einstein Telescope, and there are proposals that you could mess with them. But the other relevant bit is you can see this is at 10 to the minus 19, and this is generated for a 1 watt laser. So you can imagine you take this, you take the circulating power, call it 400 kilowatts in L4 roughly, 1 over the root of 400,000, about 2,000. Is that correct? No. It's 10 to the 5, not 10 to the 6. What is this? 200 times root 10. Anyways, so you decrease this by that amount, and then you're getting into the 10 to the minus 22, 10 to the minus 23 range. And that is that's how you get that's how you can get the shot noise down enough that you're actually, that's how much you can get the shot noise down to allow for sensitivity to gravitational waves. Okay. But then there's a second part to vacuum noise, which is how the vacuum noise couples to the mirrors themselves. I will present without commentary this formula for them. And the important bit here is it depends on the mass of the mirrors, but it also depends on the 4th power of the frequency. So that means this is going to be a low noise or a low frequency noise. You can do this math. I actually did this math myself rather than getting it from the paper. So No promises it's correct, but so you get something like this, and the important bits here are it goes as the root power, and so it increases when you increase the power, and it also has this 1/omega². So low frequency noise, but as we increase the power to combat shot noise, we're making radiation pressure noise worse. This is kind of a big trade-off. So this is how it affects. So you can see you go from just shot noise to with radiation pressure, you get this bucket, which is pretty characteristic of the LIGO noise.
That's with more LIGO like parameters, I hope.
I'm pretty sure this is. This is taken from this paper includes, among other things, examples of computing like cavity parameters with finesse at the end. That's what I took this from. Why they didn't change the labeling under Matplotlib. So yeah.
Why is the shot noise characterized as quantum noise?
Well, so it is literally vacuum fluctuations that is
Okay.
responsible for it. Yeah.
I see.
So, yeah, I'm not super familiar with the exact mechanics of it. It is admittedly in this review paper, and I admittedly did not really closely read that section. So, yeah, but
It's just come from the fact that you have that photons are, you're in a little bit like where
Yeah.
photons are discrete for this song process.
Okay.
Right?
yeah. The quote from the paper is actually that it is associated with the spontaneous annihilation and creation of the photon at all frequencies. So, yeah. So it is a vacuum process, but yeah. Okay. And so now you can get, I'm going to kind of skip discussion of most of the other noise sources because there are a lot of them, but you get something that looks like this for, I'm guessing this is 04-ish. So this is not truly 04. There are noise sources we don't understand, not reflected here, but this is sort of a breakdown of what they approximately look like. So you can see quantum vacuum is both shot noise and radiation pressure that we talked about. The Brownian noise from the coatings is now actually starting to be near the level of the shot noise where it was not previously. You have other things like suspensions. So the suspensions will have, resonant modes, and they'll have thermal noise there. These are violin modes and just other stuff happening, right? You can break this down, and this is how you get to a noise curve that looks like what LIGO actually operates with. Okay. Any questions about that? All right. So now let's get into the final part of this presentation, which is basically what are some of the design decisions that are made for modern interferometers to get us to this place. The first one is that you want a lot of power for the reasons we just laid out, but you can't really increase laser power arbitrarily without sacrificing stability. So the solution to this is to introduce what is called a power recycling cavity. Kind of simplistically, you're basically just catching the field that you would lose to the symmetric port. You're just kind of putting a mirror there to reinsert it. So this produces a Fabry-Perot cavity, and you get a gain in the power proportional to the finesse. So putting up a very high finesse Fabry-Perot cavity in, more power. Okay, and why stop there? Why not also put Fabry-Perot cavities on the arms? Get more gain in power, and you actually get more gain in power, because in addition to increasing the carrier power, you're also increasing so the sidebands get more power because the carrier has more power, and the sidebands themselves are getting amplified, so you get a lot of gain. And you also are, you're basically just increasing the length of the arm. So that's good for something that is dependent on the length of arms. And it looks like this. All well and good. But it does introduce something with complication, which is that because the cavities have pretty sharp resonant features, you would get a very sharp sensitivity, and it's not actually at the place where we want the sensitivity to be. So we introduce signal recycling, which is another Fabry-Perot cavity, but at the output port. So like this. And then, you put this on a different operating point, and that's anti-resonant, and it will re-widen the noise, or re-widen the sensitivity. So that looks a bit like this. This is the tuning, you change the tuning, and you can get to, you go from this to this. This is much more in the sensitivity range. These are the frequency ranges that we're more interested in astrophysically. There are arguments that for, say, neutron stars, you would want to detune it so that you could see, say, merge or remnant physics happening here. This is an actual thing. Alan really wants someone to write up that proposal, but anyway. So this is a thing you could do, but typically this is how we do it. Okay. And that's it. So I hope this has provided something resembling knowledge. There you have it.
Any questions? Going once? Thanks so much.
We're well under time. Automatic. Anything goes on.
I wonder how much,
Crazy, unstable.
I want to know what the